Um, we'll talk just a quick review on the repos. We'll talk about the edge use case at Sprint. It seems simple enough, but it warrants some discussion. And then we'll talk about my favorite subject, which is kind of where we're moving on. And what I mean by that is we're most interested at Sprint in terms of how we can actually develop this, not just picking on the S gateway, but how can we repeat this in 4G and the 5G network functions and components. So just a refresher, this is the functional repos. There's a few items here in general that you can think about. So when you look at really OMEC and you look at the underlying repositories, there's quite a few. So focused on deployment, focused on testing. But when we look at the network functions, we tend to have 3 repos that are in question. So C3PO, the C3PO repo that you see under OMEC actually is comprised of the VNFs you see there. We have the Open MME repository and that project, and that's also, once again, developed independently, so that's important to understand, by different teams. So that's its own repository. And then finally, we have the gateway, is what we generically refer to it. Sorry. So yeah, so we have the gateway. So there we have the control plane, data plane, but that's usually the NGIC repo, or NGIC RTC is the current repo name this year. So we also have kind of what we'll call the minimum performance kits. We've talked about this a number of times. You can download OMEC, and our expectation when you download is if you're using like the traffic tools and gens, you can get about 40,000 users. We used to have 40 to 82 CPU cores. That's a little bit dated in terms of performance, and that might have involved a certain piece of software I wrote as to why it was closer to 80 than 42. So it's closer to 42 now, as it apparently has less of my code written in it. So it's actually getting a little better each year, I guess. So with respect to the edge use case, my downstream customers did not give me an easy use case. It seems simple enough, right? So let's just select the right data termination, the right local breakout for a user. And then they added a few constraints, and that's really where things started to get a little nervous for us. So the first one was, I'm not allowed to upgrade the eNodeBs. And what I mean by that is, I'm not allowed to add things like dedicated core selection or other features that would make my life easier. So there's a lot of features we could have implemented or asked to be implemented on the eNodeBs that would have made the overall selection, slicing, and other features, not quite 5G, but pseudo-slicing, a lot easier. I was told I'm not allowed to do any of that. I have to absolutely work with what I've got. And then the other thing that they told me was I'm not allowed to change the tracking areas, nor am I allowed to change the configuration of those eNodeBs and how that's done in the network. Because one of the strategies when we talk about actually providing edge is actually make our tracking areas a little smaller and to line them up quite nicely with the edge sites. So that's one way to start actually bringing in some of the edge use cases without necessarily adding new features or new code. So we were told we're not allowed to do that. So this really then became kind of in some sense, a simple solution of what we had as far as tools to mess with. And then what I'll call a little bit of creativity in terms of, I'll call it the gray area of the specs in 3GPP. So we looked at what we had in production. So most operators will have they're referred to as a IDNS or internal DNS server that is used by the MMEs to select your S gateways. And when you implement cups, they're used to select your actual S gateway user plane. So not just the S11, but the user plane. In our case, it's also true when you go to the P gateway. Once again, when the P gateway is selecting the user plane, and we'll show that a little bit, they're using DNS. So we were looking at the tracking area DNS. The spec also has an option where you can also query by the eNodeB ID for the DNS server and select that way. Most operators today will use the tracking area because it represents multiple eNodeBs. It's less entries. It's just a lot less data to manage. So we try to have these big metro areas where we have one entry managed by the tracking area system, the tracking area ID. So we're allowed to use both in the spec. the spec is really interesting in that it says you're supposed to query it by tracking area / enode-b. And if you talk to multiple operators and the OEMs, and you ask 3GPP, what does the / mean? Does it mean you do both? Does it mean you do one? And all I got told was that is the wonderful opportunity for me to figure that out, and that 3GPP is not going to help me. So the exercise and implementation is left to the reader, so we decided to capitalize on that. Topology or top-on is a feature in 3GPP during this selection process where we can basically take something we've already selected, like an S gateway user plane, and when we're looking at a P gateway user plane selection, we could say we would like them to have very common naming. And we'll show that in a little bit, but what that does is that allows us, because this is how the SAE gateway works, this allows us to actually select the same user plane instance for the S and the P, even though in reality, really what we're selecting is an SAE gateway user plane. So in 3GPP, they treat those as 2 transactions and a string matching problem. And then finally, right, we decided we're going to maintain compliance minus this little interpretation of the /, because I'm still not sure what that means with 3GPP, and move on. So when we look at the DNS queries themselves, this is actually what it looks like. So during the request from the MME to the S gateway controller, we do get in the user location information 2 fields to execute these queries. So we get the global cell ID, and that's how we do the enode-b query, and we get the tracking area ID. And that's by rule. So you're going to see that in every initial attach on LTE. And so down below, you see the TIE DNS query that would come from the S gateway C. So there we've taken the actual tracking area information and we've added essentially the EPC information, which we already know, the MNC and the MCC are already provided. So this is all within the spec. That's the first query we send to the TIE DNS. And we also simultaneously, rather than saying it's one or the other, we simultaneously query for the enode-b. And what we're looking for is we're looking for how to handle whether we get one or both responses. And then that's going to tell us what kind of selection process we're going to do. So once again, very seemingly simple item until you start realizing there's lots of scenarios. So when we talk with operations, once again, we thought our life wasn't too bad. We figured out we were going to do the queries. And we realized then operations said, not so fast. We would like to do as little config as possible, and we're going to give you 3 scenarios. So the first one is no edge sites. Well, that's very easy. We just go back to the tracking area, to this kind of centralized data center. We do the query, and we're done. A single edge site, that's also very easy. We can use the priority system within DNS, within TripleDS, and it can select the edge site first using the priority attributes. And then if those sites are unavailable, right, they're marked out of the DNS, they will then default back. The real, and we can do those with the TIE queries. So that first query we talk about, that single tracking area query. The third scenario is actually the one that's the most interesting, and that is what happens when that central area is actually serving multiple edge sites. And so there, what we'll get back when we get the queries, we're going to get both the response from the TIE query, because that's our default location, and we're going to get back an enode-b specific response. So what we want is we want the enode-b edge site to be selected first, and then we'll run with that. And if the selection match doesn't work out, we default back to the centralized data center. So once again, we're always defaulting from an operations point of view back to that centralized data center in the event that anything is currently unavailable at the edge. Now, the good news is, once again, every individual query is basically fully compliant with 3GPP. It just happens to be that rather than saying do one or the other, we are saying please do both, and then handle in the processing. So specifically at the S gateway, what we're doing is essentially this. This is the pseudo logic. So we go ahead and determine the roles, and that's pretty straightforward. You know if you're an SAE gateway, if the APN and the P gateway information also includes you. So if you're not only the S11 interface, you're also the P gateway that's identified, congratulations, you are now an SAE gateway. That's actually how you understand that. And then following the specification, particularly the CUPS specification, we provide the 2 queries, both the enode-B and the tie query, and then based upon the response, we will actually go and actually then return the processing. Now, we did make one design decision, and that's by configuration. We envisioned that the standard tracking area DNS server may be a different database DNS server than where the enode-B information is. And part of that is the engineers, because tracking areas are fairly static and they are sometimes designed at a national level, they're designed by different teams than the regional teams. So we wanted to allow for that kind of localization to occur. And so we basically said, look, it's going to be 2 DNS queries to 2 potentially different DNS servers. So we allow for that kind of freedom to occur within the code. And this is in the code that's coming out, right, as part of this implementation. So, and then once simply, right, if there's no enode-B ID, we worry about the tie. If we have the topological processing, we keep on going with the standard process, which means we requery again for the P gateway, for the SAE gateway, or we finish our selection and we then send our signaling to the P gateway for further processing. So either way, you'll get the same end results, and that's essentially how we pull off the use case. So I'm going to pause for just a second. I'm going to move on to development. Are there any questions on the use case and what we're doing there? All right. So let's talk about development. So currently, as you can guess, it's the NGIC RTC repo that my team's working on with GS Labs. And we are still deploying virtual machines in large part because we're focused on function and not necessarily every deployment option. And I think it's important, right? I know a lot of people like to focus on function and cloud native and those sort of things. I always remind people you need some piece of software to actually deploy before you worry about how it's deployed. So kind of a chicken and egg problem. We have evolved a little bit. So when we first deployed, we focused on just trying to get enough functionality out and a little bit of automation. And now we're starting to move into construction technique research, how to define layers and stacks, and how to actually figure out how to build provable test specifications. And I think GS Labs and Sprint would tell you it's not easy. There's days where it's not fun, for sure. But we're making progress. And so as far as architectural patterns, this is probably the biggest one. This started in what is now the Open MME project. And there's a lot to see here. But basically, this is the overall pattern. It is a state machine pattern. And I'll just kind of walk through on the left here. What we have are inbound messages coming into the message library, which may be a fully functional piece of software or just maybe a sub-library that's accepting sockets and handling. And so what we do is a very lightweight protocol decode, and we'll talk about that pattern here in a little bit. But what we do is we map that to an event ID as well as the partially decoded information. We then send that to a cross-protocol state machine, so what's referred to as the event dispatcher there in the middle. And there what we're doing is we're looking for the state information we're trying to pull there. And if everything checks out there, what we then do is we take the second level decoded information and the next action, because we're trying to progress the state machine, and we actually send it to a method or event handler. Now, a lot of times, if you are familiar with like some of the older code, what we would do is if we had to send out a message, we would then dispatch that over a bus like Tapper or Trillium, send them out. The big difference here is in the event handler, if we have to fire off a timer or we fire off a protocol, we fire it directly from the thread in the event handler. So this allows us to look at single-threaded and multi-threaded architectures moving forward in the future. And then that's really, once again, the messaging library. And there's, like I said, 2 styles of messaging library. Something like Free Diameter, where it's its own app. And we're using something like a socket for communication. And then there are other messaging libraries that are directly incorporated into the main application or thread. So they're essentially making the call out to the socket themselves. Timers are treated like a protocol. So we fire timers down into a timer management, which then runs a queue. And then because we have lots and lots of timers coming in and out, what we typically do is we'll have it kind of fire back in as its own protocol. The only difference is we're clearly not decoding anything from the timer protocol. It's actually fairly straightforward. And then we're looking at things like prioritization so that we can get this. Now, this pattern has allowed us to basically build essentially multi-protocol state machine and multi-protocol test plan, which is what we're after because my team does the testing and the initial certification. And then what we're doing is it's rinse repeat. So you'll notice in red, we don't have SBA in there, but essentially we had a big question at the last ONF Connect, and that was, will we possibly kind of start over when it came to 5G? And the conclusion we came to based upon this pattern is we're just going to add another protocol and you can just keep going with 5G. It still allows you to make it a separate repo or evolve differently, but it's pretty straightforward. So this is an existing stack architecture. This is actually a free diameter, so it is its own decoder and design. And so you see once again that even though we talked about it being split right and left on the previous slide, it really is one single logical instance, and then everything to the right are those steps we talked about in the middle. As part of this, we had to make some design decisions on layering. And so what we're currently doing is we're implementing a second pattern where basically we implement the layers, single-threaded or not, and you're seeing some of the services. So application is the state machine. Peer is actually handled by the message library itself, and then transports below that. So here you're starting to see we're starting to divide then the responsibilities, and this is actually becoming quite repeatable. So our litmus test for this is following these patterns, we are able to get out of our analysis of 3GPP and our analysis for building the test plans at a much faster pace. So even if the underlying code does not reverently follow everything you see here, these patterns are working from a design perspective in terms of getting our analysts, our testers, and our coders on the same page. And that's the first item. If I can get them all on the same page, we can talk about the underlying frameworks and such later. And that's really what we're trying to go after, guys. So if you've watched a lot of the discussions that we've had on the mailing list and other items, we've talked about the long term. What should the code be? What should the language be, right? When's the right time? I mean, some of this stuff is written in C. They ask C or C++. I'm waiting for someone to ask Rust, you know, as the next item. No one's asking for COBOL yet, but COBOL or Fortran, who knows? But the other thing they ask is what framework. My personal viewpoint is this. The patterns, if we can all communicate as a community with these patterns and get work done, I'm less concerned about what the underlying framework and code is underneath, and that's really what we're pushing for. And you're gonna start seeing sprints really advocate these types of patterns across all of the repos within OMEC, even if the underlying implementations are quite different. So anyway, that's kind of where we're evolving on the construction techniques. The other side is, and I got the question again today, automation. Yes, we're still automating. So at this point, diameter since 2017 is automated. We start with a Word document or a text document. We then go in, we cross-compile, we correct, and we generate the structural code. At this point, we are also generating now GTPC from the specs themselves, and we are also capable of generating PFCP from the specs themselves. The idea here is rather than assigning a developer to augment the existing code, we pull in the existing documents, the latest documents, we run the processing. If there's a major error, we send it back to 3GPP to be fixed, and we gen the code. The other good news is it used to be like an hour to an hour and a half in the first couple generations to do anything. We're now down to 6 seconds. So, and that 6 seconds, most of that time is actually unzipping the file. It takes about a second or two now to actually parse the actual 3GPP specs, extract the structural information, do a validation, and then push it forward. So anyway, that's where we're at as a whole. We're getting better at that. And so in summary, right, we're looking at the edge selection sites. our approach is heavily patterns-based at this point to get the code moving. And really, our focus is the NGIC, RTC libraries, and compliance. And as you can tell, we want to improve the way the functions are being built, and we want to get better and faster at it. And so we feel like that. Timeline-wise, we'll see the code in my lab toward the end of this year. And then I always remind people, just because my team accepts it doesn't mean my downstream partners do. They have their own processes, and they are independent organizations. So we hope to see things sooner than later, but that's not always the case. But we'd like to get it out into the repos once we have acceptance within my team. So with that, I don't know if I have time for a question or two, but yep.